In recent times, humanity has accomplished remarkable achievements in space exploration. We've set foot on the moon, sent robots to Mars, and launched probes to the farthest reaches of our solar system. Yet, despite these successes, we remain confined within our cosmic neighborhood. Have you ever wondered why we've been able to explore nearby planets but can't venture beyond them? In today's exploration of space science, we'll examine the current limits of space travel and understand why interstellar journeys remain in the realm of science fiction. From spacecraft speed to the immense energy required, the obstacles are far more daunting than most people realize. We'll explore these challenges and what must be overcome for us to someday reach other stars. Revealing why this dream remains so distant, the history of space exploration is filled with extraordinary milestones. In the late 1950s, driven by the Cold War space race between the US and the Soviet Union, we took our first steps into space. The launch of Sputnik in 1957 marked the beginning, and in 1961, Yuri Gagarin became the first human to orbit Earth. These milestones showed that escaping Earth's atmosphere was possible and paved the way for crewed missions. The crowning achievement of that era came in 1969 with the Apollo 11 mission, humanity's first steps on the moon. That accomplishment sparked dreams of reaching other planets. Over time, however, the focus shifted toward uncrewed missions. We sent probes to distant planets, with notable successes like missions to Mars and the continued study of Jupiter and Saturn. Voyager 1, launched in 1977, is now over 20 billion kilometers from Earth and at the edge of interstellar space, yet still far from the nearest star. This highlights how vast space truly is and how limited our technology remains. Despite all we've achieved, we are still confined to our solar system. The most significant challenge of interstellar travel is distance. Even within our solar system, the scale is enormous. Earth is about 150 million kilometers from the Sun, one astronomical unit. Voyager 1 took over for decades to reach the edge of our solar system and still hasn't fully left it. To reach another star like Proxima Centauri, which lies about 4.24 light-years away, a spacecraft moving at Voyager's speed would take approximately 70,000 years. Even using advanced ideas like laser-powered solar sails, we'd only achieve a small fraction of light speed, and the journey would still take decades or centuries. These long timelines are one reason interstellar travel remains theoretical. Another major obstacle is propulsion. As distances grow, it's not just about going faster. The energy needed increases dramatically. Our current propulsion methods, such as chemical rockets using hydrogen and oxygen, work well for short trips, but are inadequate for interstellar voyages. Carrying the required fuel becomes unfeasible. Research into ion propulsion, which uses charged particles to generate thrust, shows promise in efficiency but results in very slow acceleration, useful only for long-duration, low-thrust missions, like asteroid exploration. Fusion propulsion, which could theoretically produce enough energy to travel faster, remains beyond our technical reach. Compact, space-worthy fusion reactors have yet to be developed. Other futuristic ideas, such as solar sails and laser propulsion, are being explored. The Breakthrough Starshot project envisions sending tiny probes to Proxima Centauri using lasers to push reflective sails. If successful, they could reach 20% the speed of light and arrive in 20 years. However, it faces enormous hurdles, from laser precision to probe durability and especially deceleration at the destination. In short, propulsion remains an unsolved challenge. Energy is another fundamental barrier. Solar power, while effective near the sun, becomes virtually useless farther out. Nuclear energy, used in spacecraft like Voyager and New Horizons through radioisotope thermoelectric generators, RTGs, offers more consistency over long missions, doesn't generate enough power for advanced propulsion. Even if we solved both propulsion and energy, we would still face the biological and psychological challenges of human survival on multi-decade or even century-long missions. Long-duration space travel carries serious health risks. Outside Earth's magnetic shield, cosmic and solar radiation increase the chance of cancer and can damage the nervous system and internal organs. While researchers are exploring radiation-absorbing materials and shielding, no current method offers reliable protection for such long missions. Microgravity is another threat, causing muscle and bone deterioration. Even with regular exercise, it's difficult to fully counteract these effects. Mental health is also a concern. Astronauts on short missions already face psychological strain due to isolation and confinement. Imagine a crew confined to a small ship for decades, with no external contact aside from their crewmates. Depression, anxiety, and other issues would be almost inevitable. Communication adds yet another complication. Even within the solar system, messages can take minutes or nearly an hour depending on planetary alignment. With Proxima Centauri, a single message would take over 4 years to reach its destination, and for more to receive a reply. This delay makes real-time interaction impossible. Then there's the issue of time itself. Interstellar journeys could take hundreds or thousands of years, depending on the technology. One proposed solution is the generation ship, a massive spacecraft where several generations live and die before reaching their destination. But this idea is fraught with logistical and ethical questions. How do you ensure the ship remains functional over centuries? How do you motivate future generations born aboard, who never chose to take part in the mission? Another theoretical idea is hibernation or cryogenic sleep, slowing biological functions to allow the crew to sleep through the trip. But this remains purely science fiction. We have no way to safely suspend and later revive humans for such extended periods. Even more exotic ideas like warp drives, wormholes, or space-time manipulation exist only in theory, with no practical foundation. Einstein's theory of relativity adds a further twist: time dilation. As spacecraft approach light speed, time slows for the travelers relative to those on Earth. So, while only a few years might pass for the crew, decades or centuries would pass back home. This creates a disconnect that makes round-trip travel or interstellar colonization even more complicated. A ship traveling at near light speed would essentially become its own isolated civilization. All of this leads to a sobering reality. Interstellar travel, while inspiring, remains far beyond our current capabilities. Space exploration is still in its infancy, and exploring even our solar system in detail may take millennia. As for the Fermi paradox, if the universe is vast and full of life, where are all the aliens? The simplest answer may be that, like us, other civilizations are also stuck in their own stellar neighborhoods. The universe's vast distances make travel between stars nearly impossible, regardless of intelligence or technology. This doesn't mean aliens don't exist. It just means they, too, might face the same cosmic limitations. No warp drives, no shortcuts, only the slow, steady march of science. What do you think? Does the universe truly prevent us from exploring it the way science fiction imagines? Or might an unknown discovery someday unlock the stars for us? Let us know your thoughts, and if you enjoyed this deep dive, don't forget to like the video and subscribe for more. Thanks for watching, and see you next time.